Welcome to the Explainer. Today we're actually traveling a bit into the future. Well, looking at a really fascinating snapshot of developer problem solving from a diary entry dated May 15th, 2026. We're following the notes of a developer named Ang, who's working through a super specific yet honestly incredibly relatable programming challenge in Haskell. If you've ever hooked up an external library to your app and suddenly felt like you just lost all visibility into what was happening under the hood, yeah, this one is going to resonate with you. We're going to see exactly how Ang bridged the gap between their own application's logging and the internal logging of a pretty powerful external tool.
Okay, let's dive into this. The whole inciting incident here is a classic developer dilemma. How exactly do you see inside a black box? Because, when you're building a CLI application, you completely control the feedback loop. You decide what gets printed to the console and what stays hidden. But the very second you hand off processing to a massive, complex external library, poof, that visibility just vanishes. If something goes wrong, or if you really just want to understand the flow of data, you absolutely need a way to surface those internal debugging logs from the library right up to your user. Otherwise, you're literally just staring at a silent failure.
To ground this abstract concept in a concrete task, Ang basically hit a wall while building one very specific feature, generating PDF ebooks via Typest. Now, Typest is a highly capable typesetting system, but for this particular workflow, Ang is relying on the Pandoc library to handle the heavy lifting of the document conversion. And while putting this ebook generation feature together, Ang realized they desperately needed a way to see Pandoc's internal debugging logs. Without them, troubleshooting that Typest output was basically just guesswork. So the goal became crystal clear: extract those hidden Pandoc logs and bring them into the light of the main application.
Now, you might be wondering how to actually pull that off. The most straightforward approach to this wasn't some crazy complex interception of data streams. It was actually a simple, elegant mapping based on a verbosity dial. Think of your CLI application as having a volume knob for its logs, right? That's your verbosity level. Well, Pandoc has its own internal speaker system with its own volume settings. So the solution here is essentially wiring your app's volume knob directly to Pandoc's internal speaker. This way, when a user cranks up the logging detail on the main app, Pandoc automatically gets louder too.
So how exactly do we build this bridge? Ang's diary breaks it down into 3 rapid-fire steps. Step 1, import the logging types, because our app needs to speak Pandoc's language. Step 2, map the integers. We have to translate our app's numbers directly to Pandoc states. And step 3, update the I/O function, which just passes that setting right into the execution pipeline. Let's actually look at the code diff to see this in action.
All right, step 1 is all about grabbing the right tools for the job. In the diff Ang provided, we can see a new import statement tacked on to the top of the file, importing verbosity from text.pandoc.logging. This pulls in the verbosity data type straight from Pandoc. Alongside this, Ang also updated the primary text.pandoc import to include a function called setVerbosity. These two additions, they're the absolute foundational pieces you need to even start talking to Pandoc about how loud its logs should be.
Moving right along to step 2, let's see how this builds into the core logic. Ang created a translation matrix using a new function called getPandocVerbosity. It's super straightforward. If the CLI app passes a 0, it maps directly across to Pandoc's error level. If it passes a 1, it maps to warning. And for literally anything else, which is represented by that underscore wildcard, it maps to info. It's just a clean, direct translation matrix that makes sure the external library behaves exactly as the user expects based on what they typed into the CLI.
Finally, we got to inject this mapping into the actual execution pipeline. So Ang updated the convert to ebook function. Before this, that function just took the input path and the output format from the app's arguments, and that was it. Now, Ang modified the function signature to pull out the verbosity argument as well, binding it to the variable v. By plucking out this v right at the exact moment the ebook conversion is triggered, the application can pass that specific volume level down into the Pandoc process. And boom, the gap between the two systems is successfully bridged.
Section: A question of style. Equations versus case expressions. Now, as with any good programming diary, solving the functional problem is really only half the fun. The other half is reflecting on exactly how that problem was solved, looking at the aesthetics and structure of writing Haskell code. And this brilliantly illustrates the kind of choice developers face every single day. On one side, we have the way Ang initially wrote it. Multiple function equations. You define getPandocVerbosity 0, then on a totally new line, getPandocVerbosity 1, and so on. It reads like a list of rules. On the flip side, Ang notes that some developers might prefer to rewrite this into a single case expression. In that style, you define the function just once. Get Pandoc verbosity v equals case v of, and then you list all the mappings underneath it. The thing is, both approaches achieve the exact same technical outcome, mapping an integer to a verbosity state.
So why would you choose one over the other? Well, Ang points out that the real benefit of using a case expression shines when your code steps out of simple, everyday mappings and into much more complex logic. Like, do you need a do block to sequence actions? Case expression. Are you handling complex types like maybe or either that carry potential failure states? Case expressions absolutely excel there. Or maybe you need where clauses or let bindings to organize helper functions and temporary variables. Those all integrate super neatly within a single case expression structure to just keep everything nice and tidy.
But, and honestly this is a crucial takeaway from Ang's notes, we aren't dealing with complex maybe types or elaborate do blocks here. We are dealing with a simple mapping of an integer to a single word. Because of that sheer simplicity, Ang concludes, and I quote, "For our example here, both patterns work perfectly fine. When the mechanical demands of the code are this lightweight, the decision literally stops being about strict technical superiority. It completely becomes a matter of personal style and readability."
Which brings us to a really compelling final thought to leave you with today. When you sit down to write or review code, how much of what's on the screen is an absolute necessity dictated by the rigid logic of the system, and how much of it is simply a reflection of your own personal style? As Ang's diary entry shows us, even in the highly structured world of Haskell, bridging external libraries and managing internal logs ultimately leaves a lot of room for the developer's human touch. Thanks for joining me for this explainer, and keep exploring the fascinating choices behind the code.